Everything you were taught about gravity is technically wrong, not slightly off, not a useful approximation that we quietly correct later. Wrong in a way that changes what you think reality is made of. And here's the strange part. The wrong version feels more intuitive. It feels obvious. It feels like something you can trust, and that's exactly why it's so hard to let go of. So let's start with what you think you know. An apple falls. A planet orbits. The moon circles the Earth. And in every single one of these cases, you are told the same story. Gravity is a pull, a force reaching out across space, grabbing objects, dragging them together. Isaac Newton described it, quantified it, gave us equations for it. And those equations work. They're still used today to launch rockets and land spacecraft with extraordinary precision. But precision isn't the same as understanding. And here's the question nobody asked in your physics class. If gravity is a pulling force, what exactly is doing the pulling? What is the medium? What is the mechanism? Newton himself admitted he had no answer. He called it action at a distance and essentially said, I don't know how it works, but here's how to calculate it. That gap, that unexplained how, stayed open for over 200 years until someone closed it. And the answer was nothing like anyone expected. Pause and predict what happens next before we go further. If gravity isn't a pulling force, if there's no invisible rope connecting the apple to the earth, then what is actually happening when something falls? Think about that for a moment, because the answer is going to require you to rethink something more fundamental than gravity itself. It's going to require you to rethink what space is. Here's where the intuition starts to crack. You probably think of space as a container, an empty, neutral stage where matter exists and events happen. Space is just there, passive, invisible, unaffected. Objects move through it, but space itself does nothing. That assumption is wrong. Space, or more precisely, space-time, is not a passive background. It is a physical structure, and like any physical structure, it can be shaped. It can curve. It can bend in response to mass and energy. And when it curves, it changes the geometry of the paths that objects travel. This is a simplified explanation to make the core idea intuitive, but it's also far closer to the truth than any invisible pulling force. Think of it this way. Imagine a large, flat rubber sheet stretched tight and held at the edges. Now place a heavy bowling ball in the center. The sheet deforms. It curves downward around the ball. Now roll a marble across the sheet. Instead of traveling in a perfectly straight line, the marble curves toward the bowling ball. Not because the bowling ball is pulling it, but because the geometry of the surface it's traveling on has changed. That's gravity, not a pull, a curve. But notice something here, and this is where most explanations quietly cheat. The rubber sheet analogy already assumes gravity. The bowling ball dips downward because Earth's gravity is pulling it. So the analogy is using gravity to explain gravity. It's circular. The real situation is stranger and more complete than any analogy can capture. Because it's not just space that curves, it's time. And this is where things get genuinely unsettling. When mass curves space-time, it doesn't just bend the spatial dimensions, it bends time itself. The closer you are to a massive object, the slower time moves for you relative to someone farther away. This isn't science fiction, this isn't a thought experiment. It is a measured, confirmed physical phenomenon. Your GPS satellites experience this right now, every second of every day. The satellites orbit high above Earth, farther from Earth's mass, where space-time is less curved. This means their onboard clocks run slightly faster than clocks on the surface, by about 45 microseconds per day. That's a tiny number, but if it weren't corrected for, your GPS would accumulate errors of roughly 10 kilometers per day. The engineers who built the system had to account for space-time curvature, for the geometry of time itself, just to make navigation apps work on your phone. This is not abstract. This is infrastructure. Now here's the deeper piece that most people never reach. When an object falls, when an apple drops toward the Earth, it isn't being accelerated in the way you normally think of acceleration. From the object's own frame of reference, it's doing something remarkable. It's following the straightest possible path through curved space-time. Physicists call this a geodesic. On a flat surface, a straight line is obvious. On a curved surface, say the surface of the Earth, the straightest possible path between 2 points is a curve. Planes flying long distances follow these paths, which is why a flight from New York to London arcs over Greenland rather than cutting directly east. That arc is the straight line on a curved surface. Falling objects are doing the exact same thing. They are following the space-time equivalent of a straight line, a geodesic through curved geometry. There is no force reaching out and grabbing them. They are simply moving as freely and as naturally as anything can move. The curvature of space-time is what creates the appearance of a pull. Pause and predict what happens next. If falling is actually moving in a straight line through curved space-time, what does that make you feel right now, standing still on the surface of the Earth? Here's the twist that most people never hear. You, right now, are not in free fall. You are being accelerated. The ground beneath your feet is pushing up against you constantly, preventing you from following your natural geodesic through space-time. From the perspective of general relativity, the person in free fall, the skydiver, the astronaut in orbit, is the one moving inertially, freely, without any force acting on them. You, sitting or standing on solid ground, are the one experiencing a real force. The normal force of the ground pushing up against the curve of space-time you'd naturally follow. This is the moment in the script where the emotional floor drops, because it means that everything we called feeling gravity, the weight in your legs, the heaviness in your chest after a long day, that sensation is not gravity at all. That sensation is the ground refusing to let you fall. That is the resistance. Gravity, in the relativistic sense, is what you feel when nothing is touching you. The astronaut floating weightlessly in the International Space Station is not escaping gravity. Earth's gravity is still very much present up there. It's what keeps the station in orbit. What the astronaut has escaped is the ground. They are in pure freefall, following a geodesic around the Earth, and so they feel nothing, no weight, no pull. Just the geometry of space-time, quietly doing what it always does. This should feel wrong. It should feel counterintuitive. Hold on to that feeling. It means you're actually understanding something real. Now, 4 common things people believe about gravity, woven into what we've already covered. Many people believe that gravity is stronger in space, near massive objects, because it reaches farther. But gravity doesn't reach. Space-time curvature is geometry, and geometry is local. Every region of space-time has its own curvature based on the mass and energy present. Many people believe that weightlessness means no gravity. The astronaut example already dissolved that one. Many people believe Einstein replaced Newton. He didn't entirely. Newton's equations are still accurate within the limits of weak gravitational fields and slow speeds. General relativity is the more complete description, but Newton is still inside it, like a close approximation inside a larger truth. And many people believe that if gravity is geometry, it must be purely a mathematical idea, something abstract with no physical consequence. The GPS satellites are a permanent answer to that belief. So what is gravity, finally? In the fullest sense we can currently say, it is the curvature of space-time, 4-dimensional geometry shaped by the presence of mass and energy. Objects don't get pulled, they follow the natural shape of the space and time around them. What we experience as gravitational force is the sensation of not following that shape, the surface beneath us constantly redirecting us away from our natural path. The universe is not full of invisible strings. It is full of curves, and those curves are the physics. There is still a frontier here. General relativity and quantum mechanics, the 2 most successful theories in the history of science, do not agree about what gravity is at the smallest scales. Whether gravity is also carried by a particle, a graviton, whether space-time itself is quantized, these questions are genuinely open. The story is not finished, and that might be the most honest, most important thing physics can tell you. The map is not the territory, and we are still drawing. Reality is not what you were taught. It is stranger, quieter, and far more geometric than anyone expected. The ground is not keeping you safe. It is keeping you from falling freely through the curved shape of time itself.